something existed before the universe began. Not stars, not space, not even time. Something that breaks every rule of logic we trust today. And the strange part is this: physics does not fully deny it. In fact, some of the most advanced ideas in modern cosmology quietly point toward it. For decades, scientists have described the origin of everything using one name, the Big Bang. It is the most accepted explanation for how the universe expanded from an extremely hot, dense state into everything we see today. Galaxies, planets, time itself. But here is what most people do not realize. The Big Bang Theory does not actually explain the true beginning. It explains the earliest moment we can currently describe with physics. It tells us how the universe evolved after it was already in motion. It does not fully answer what caused it or whether there was something before it. As we push the equations backwards, something strange happens. The laws of physics begin to break down. Gravity becomes infinite in the math. Space and time lose their normal meaning. This is what scientists call a singularity. But many physicists believe this is not a real physical point. It is a signal that our current understanding is incomplete. At this edge of knowledge, the universe becomes silent. The equations stop working, and that silence is where the mystery begins. Brian Greene, one of the most respected theoretical physicists in the world, has spent decades exploring these boundaries of reality. His work in string theory and cosmology often focuses on what lies beyond the limits of what we can currently observe or test. According to this line of thinking, the Big Bang may not be the absolute beginning of everything. It may only be a transition point from something deeper and more complex. This idea changes everything. Because if the universe did not begin at the Big Bang in the way we assume, then the question shifts. We are no longer just asking how the universe expanded. We are asking what existed in the most extreme conditions possible, before space had shape, before time had direction, before cause and effect had meaning. And that leads to one of the most unsettling questions in modern physics. If time itself began at the Big Bang, then what does the word before even mean? In everyday life, time feels simple. One moment leads to the next, because comes before effect. A clock moves forward in a straight line, but at the deepest level of reality, this may not be fundamental at all. Some theories suggest that time itself could be something that emerges from a more basic structure, something that does not behave like time at all. This means the early universe might not be a story that begins at a single point. It could be something far more unusual, a state where the rules we rely on simply do not exist yet, a condition where reality is not separated into past and future, a condition where change does not follow sequence. Modern physics does not have a final answer for this, but it does have ideas. Some of them are deeply unsettling because they suggest that the beginning of everything may not be a beginning in the way our minds understand it. There are models in which the universe does not start from nothing, but from a prior quantum state. Others suggest the universe may not have a true edge in time at all. Instead, it could be part of a larger structure where what we call the beginning is only a shift in form, not the start of existence. Each of these ideas points toward the same conclusion. The origin of the universe is far more mysterious than most people realize. In this video, we will explore these frontiers of science step by step. We will look at why the Big Bang Theory reaches its limits. We will examine what physics says about time itself. We will uncover the strange possibility of a reality that existed before the universe as we know it. And we will break down why leading scientists like Brian Greene believe the true origin of everything may be far more complex than a single beginning event. By the end, you may see the universe in a completely different way, not as something that started from nothing, but as something whose origin is still hidden behind the deepest mysteries in physics. Welcome to the channel. If you want to explore more deep science stories like this, subscribe and stay with us. The Big Bang is often spoken about as the beginning of everything, but But in physics, that is not exactly what it means. The theory describes how the universe expanded from a state of extreme density and temperature. It explains how space stretched, how energy cooled, and how matter formed over time. It does not fully describe the absolute origin of that state. When scientists run the equations backward, the universe becomes smaller, hotter, and more extreme. At a certain point, the known laws of physics stop behaving in a reliable way. This is not a minor gap. It is a complete breakdown of the equations that normally describe space, time, and gravity. The most important limit appears at a point called the Planck time. This is the earliest moment in cosmic history that physics can meaningfully describe. It is an incredibly small fraction of a second after the expansion began. Before this point, current models lose their predictive power. Space and time themselves are thought to behave in ways that are not yet understood. At this scale, general relativity, which describes gravity and the structure of the universe, no longer works properly. It predicts a singularity, a state where density becomes infinite and the laws of physics stop making sense. But most physicists do not believe this represents a real physical object or event. Instead, it is treated as a warning sign. It suggests that the theory is being pushed beyond its limits. This is one of the lesser-known facts about the Big Bang. The famous beginning point is not a confirmed physical reality. It is a mathematical result that appears when current equations are stretched too far. It is similar to dividing a number by 0. The result is not meaningful, but it signals that something deeper is missing from the calculation. In modern cosmology, this is a major problem. The universe at its earliest stage should be described by both general relativity and quantum mechanics. But these two frameworks do not agree under extreme conditions. General relativity describes gravity as smooth and continuous. Quantum mechanics describes reality as uncertain and discrete. When both are applied together at the beginning of the universe, they produce contradictions. Scientists have tried to merge these ideas into a single theory of quantum gravity, but no complete version has been confirmed yet. Without it, the true nature of the earliest universe remains hidden. This is why the initial singularity is not accepted as a final answer. It is more like a placeholder, a point where our understanding collapses, not necessarily where reality begins. Some physicists believe that if a better theory replaces it, the singularity may disappear entirely from the equations. That possibility changes the entire picture. It means the universe may not have started from a point of infinite density at all. Instead, that extreme condition may be a sign that we are missing a deeper layer of physics, a layer that could explain what truly existed before the expansion began and why the known laws of nature fail at that edge of time. One of the most unsettling ideas in modern cosmology is that time itself may have a beginning. Not just the universe, not just matter, but time. In everyday experience, time feels like a constant flow. One moment follows another in a straight line. Past, present, and future seem fixed in structure. This structure is so familiar that it feels absolute. But at the deepest level of physics, this assumption may not hold. According to standard cosmology, time as we know it is tied directly to the expansion of the universe. As the universe expands, time moves forward. As we trace the universe backward, space shrinks, energy becomes denser, and time approaches a boundary. That boundary is the Big Bang. At that point, something strange happens. The equations of physics no longer describe a normal flow of time. They suggest that time itself may stop having meaning. Not just difficult to measure, not just unclear, but fundamentally undefined. This leads to a difficult question. If time begins at the Big Bang, then what does the word before actually refer to? In many scientific models, before requires time to already exist. Cause and effect depend on it. One event must occur earlier than another for causality to make sense. But if time itself starts at the Big Bang, then there is no earlier moment in the usual sense. There is no timeline extending backward. There is no sequence leading into it. Some physicists describe this as a breakdown of causality. The idea that every event must have a cause becomes meaningless if there is no time in which causes can exist. This does not mean events occur without explanation. It means that the structure we use to describe explanation may not apply at the boundary of the universe. There are also deeper theories that challenge the idea of time as a fundamental feature of reality. In some approaches to quantum gravity, time is not treated as a basic building block. Instead, it is seen as something that emerges from more primitive relationships between physical states. In this view, time is not something that exists on its own. It is a pattern that appears when the universe reaches a certain level of complexity. This idea is difficult to reconcile with intuition. It suggests that at the most fundamental level, reality may not contain a ticking clock at all. Instead, it may consist of static relationships that only appear to evolve when viewed from a higher level. If this is true, then the early universe may not have a before in any meaningful sense. There would be no earlier stage waiting behind the Big Bang. There would only be a boundary where the concept of time stops applying. This creates a paradox that science is still struggling with. If causality depends on time and time depends on the universe, then the origin of the universe sits outside the framework that defines origin itself. Explanations begin to lose their usual structure. Cause and effect no longer form a chain. They become part of something more abstract, where the usual rules of sequence may not exist at all. When the universe is pushed to its earliest moments, classical physics begins to fail. The rules that describe planets, stars, and galaxies no longer work in the same way. At that level, quantum mechanics takes over. And quantum mechanics does not deal in certainty. It deals in probability. In the quantum world, nothing is fixed. Particles do not have exact positions until they are measured. Energy can appear and disappear in extremely short intervals. Even empty space is not truly empty. It is filled with constant fluctuations, where particles briefly come into existence and then vanish again. This background activity is not a theory of speculation. It is supported by experiments in quantum field physics. When scientists apply these ideas to the early universe, a new picture begins to form. Instead of a clean beginning from absolute nothing, some models suggest a quantum state that existed before classical space and time emerged. This state is not like anything in everyday reality. It is not space. It is not time. It is not matter in any familiar sense. It is a set of quantum conditions governed by probability rules alone. From this perspective, the Big Bang may not be the start of existence. It may be the moment when a quantum state shifted into something more stable, a transition from a purely quantum phase into a classical universe where space and time became defined. One lesser-known idea in quantum cosmology is that the universe could have originated from a quantum fluctuation. In simple terms, a fluctuation is a temporary change in energy that appears without a clear cause in the classical sense. In quantum field theory, these fluctuations are normal and constantly happening at microscopic scales. Some models extend this idea to the entire universe, suggesting that a fluctuation in a pre-existing quantum state could have triggered the birth of space-time itself. This idea changes the meaning of nothing. In everyday language, nothing means absolute emptiness. No space, no energy, no structure. But in physics, especially quantum physics, nothing is not truly nothing. The lowest energy state of a quantum field still contains activity. It still contains structure at a fundamental level. It still obeys laws. This means that even the most empty state known to physics is not a void in the philosophical sense. It is a structured background with hidden activity that cannot be removed entirely. Some theories suggest that this quantum background could exist without time in the way we understand it, without classical space, without defined objects, only mathematical relationships and probabilities. From within that framework, a transition could occur that gives rise to space, time, and energy as we experience them. The most striking part of this idea is that the origin of the universe may not require an external cause in the traditional sense. In quantum mechanics, certain events do not need a classical trigger. They occur because of inherent probabilities built into the structure of the system itself. This leads to a strange possibility. The universe may not have emerged from a moment of absolute nothingness. It may have emerged from a deeper quantum reality that never contained nothing in the way it is usually understood. Some of the most advanced ideas in cosmology challenge the idea of a clear beginning altogether. Instead of a sharp starting point, the universe may have no defined edge in time. This idea comes from models that treat space and time as a single connected structure called space-time. In this framework, the universe is not just expanding through space. It is also shaped by the geometry of space-time itself. And that geometry may behave in a very unusual way near the earliest moments. One of the most famous approaches is known as the no-boundary proposal. It suggests that the universe does not have a boundary in time, just like the surface of a sphere does not have an edge. On a sphere, you can travel in one direction and never find a starting or ending point. There is no sharp edge where motion suddenly stops. The surface simply curves back on itself. In a similar way, space-time in the early universe may curve in such a way that the concept of a first moment disappears. Instead of a point where everything begins, there is a smooth transition where time gradually behaves differently. Near that region, time may act more like a spatial dimension. It does not flow in the usual sense. It blends into a structure where direction loses meaning. This idea is not just philosophical. It comes from attempts to combine quantum mechanics with general relativity. In certain mathematical solutions, the equations allow a universe that is finite but has no boundary. It is complete, yet it does not require a starting edge. A lesser-known implication of this model is that the classical idea of a singular beginning is replaced by a smooth geometry. The extreme conditions of density and temperature are still present, but they do not occur at a single point in time. Instead, they are spread out in a region where time itself becomes fuzzy and less defined. In this view, asking what came before the universe becomes similar to asking what lies north of the North Pole. The question loses meaning because the structure of space-time does not support an extension in that direction. Other alternative models in cosmology also support similar conclusions. Some versions, quantum gravity, suggest that space-time is not fundamental but emergent. In these cases, the early universe is not a place where time suddenly begins. It is a phase where the concept of time gradually becomes valid as the universe evolves into a classical state. There are also models where the universe undergoes a bounce instead of a beginning. In these scenarios, a previous universe collapses and transitions into expansion. The Big Bang becomes a midpoint rather than an origin. Even here, the idea of a sharp starting boundary is replaced by a continuous process. Across these different approaches, a pattern appears. The early universe does not behave like a single point of creation. It behaves more like a transformation in structure, a shift in geometry, a change in the way reality itself is organized. If these ideas are correct, then the universe may not have a first moment in the traditional sense. Instead, it may exist as a self-contained system where beginnings are not edges, but smooth transitions hidden within the fabric of space and time itself. Some of the most intriguing ideas in modern cosmology suggest that the Big Bang may not be a true beginning at all. It may be part of a much larger process that extends far beyond a single event. One set of theories describes a cyclic universe. In this view, the universe goes through endless phases of expansion and contraction. It expands, cools, and forms galaxies. Then, over extremely long time scales, gravity may reverse the process. Everything could slowly collapse back into an extremely dense state. After that, a new expansion begins again. This idea is often called a bouncing universe model. It replaces the idea of a single origin with a repeating cycle. Each cycle begins with what looks like a big bang, but it is not the absolute start. It is a transition from a previous phase. Some versions of this model suggest that traces of earlier cycles could, in theory, leave subtle imprints in cosmic radiation. Although no confirmed evidence has been found, there is another possibility that goes even further. Instead of one universe cycling through time, there may be many universes existing at once. This is known as the multiverse concept. In some versions of inflation theory, space expands in a way that creates separate regions of reality. Each region can become its own universe, with its own physical laws, constants, and history. Our observable universe would then be only one bubble in a much larger cosmic structure. A lesser-known detail in these models is that different universes might not share the same physical rules. The strength of gravity, the behavior of particles, or even the number of dimensions could vary from one universe to another. This makes the concept of a universal origin even more complex, because there may not be a single starting point shared by everything. In this framework, the Big Bang is not the beginning of all existence. It is the beginning of our local region of space-time. Other regions may have their own separate beginnings, or may exist in states that never experience a beginning in the way we understand it. Some advanced theories in quantum cosmology suggest that these universes could be connected at a deeper level through a shared underlying structure. This structure is sometimes described as a higher dimensional space or a fundamental quantum field from which multiple universes emerge. If this is true, then the idea of a single origin moment becomes less meaningful. The Big Bang would not represent the creation of everything. It would represent a phase change within a larger system, a shift from one state to another within a broader reality that extends beyond what we can observe. Across cyclic models and multiverse theories, a common pattern appears again. The universe does not point clearly to one beginning. Instead, it suggests a deeper structure where beginnings may be local events, not absolute ones. Each model replaces a single origin with something continuous, repeating, or distributed across a much larger cosmic framework. The true origin of the universe remains one of the deepest unsolved problems in physics. Every direction scientists take leads to more questions instead of final answers. The closer we get to the beginning, the less clear the idea of a beginning becomes. The Big Bang still stands as the best description we have for how the universe expanded into its current form. But as this journey shows, it may not be the full story. It may only describe a transition from something deeper, something that current physics is not yet able to fully explain. Across different models, a strange pattern appears again and again. Time itself may not extend endlessly into the past. It may start at a boundary where the rules of physics change, or it may not exist in the fundamental sense at all. Space-time may curve, shift, or emerge from something more basic, where the idea of a first moment loses meaning completely. At these extreme scales, reality stops behaving in ways that match everyday logic, because in effect become unclear. Time may lose its direction. Space may not be a fixed stage where events happen, but something that forms only when conditions are right. Even the idea of before becomes unstable when time itself is no longer guaranteed. This is where modern cosmology reaches its limit, not at a clear answer, but at a boundary of understanding. A place where mathematics still works in parts, but no longer gives a complete picture of reality. And at that edge, science does not find certainty. It finds possibility. Across quantum models, cyclic universes, and multiverse theories, one idea keeps returning. The beginning of everything may not be a true beginning in the way it feels from inside the universe. It may be a shift, a transformation, a change in state from something that existed in a form we do not yet understand. And that leaves a powerful thought behind. The universe may not have started the way it appears from our perspective. It may simply have changed state into what we now call existence. a silent transition hidden behind the deepest layers of physics still waiting to be fully uncovered. If you enjoyed this journey into the edge of reality, subscribe to the channel and stay with us. There is much more to explore beyond what we think we already know.